This is a talk entitled Lessons from Quantum Mechanics. It's a representation of a talk given on the 19th of April 2015 at the Center for Sacred Sciences in Eugene, Oregon. The center has a mission that consists of three parts. The first is to demonstrate that there's a common universal truth at the core of the world's major religious traditions. A second part of the mission is to foster a community of spiritual practitioners who wish to follow this universal teachings of the mystics. And the third part of the mission relates to this talk, and that's to help develop a new worldview in which the truths of science and the truths of mysticism are seen as different ways of viewing the same underlying reality. Just as spiritual teachings are not ultimate truths, but are skillful means to guide people towards the ultimate truth and also to help us live in a more harmonious way in the world, a new worldview will help society as a whole to do that as well. It will point beyond itself to a transcendent truth, and it will also provide a context in which hopefully people can live more harmoniously, and also provide a context in which the teachings of the mystics can be seen as compatible with the teachings of science. So what is the relevance of quantum mechanics? Well, in the context of its relationship with spiritual traditions, we've seen in popular culture books like The Tao of Physics, my own book, Einstein and Buddha, and these have drawn parallels between some of the Eastern philosophies and the sayings of modern quantum physicists. Now, these are intriguing and provocative parallels, but they don't really prove anything on a deep level. They don't lay a solid foundation for a real integration of the two. They don't provide scientific justification for mysticism. These are parallels between specific interpretations of quantum theory and between specific teachings in particular Eastern philosophies. But quantum mechanics does perhaps teach us some deeper lessons that can help provide a more solid, enduring foundation for connecting science and spirituality. So what is quantum theory? We should say first of all that it's one of the best confirmed scientific theories ever. It's the basis for understanding of atomic and subatomic phenomena and the materials of which they're made. It's the basis of microcomputers, laptops, cell phones, GPS, lasers, CDs, DVDs, LEDs, digital cameras, solar cells, nuclear energy, diagnostic imaging techniques such as MRI and PET. So it's really the foundation of so much of modern technology. It's really pervasive. And despite the challenges with understanding the meaning of quantum theory, as a science itself, it's extremely well confirmed, the best confirmed theory of science ever. Now, to understand the significance of quantum theory, it's also helpful to see how it fits within the context of modern physics. Modern physics began with classical mechanics developed primarily by Newton. Now, some phenomena could not be explained by classical mechanics, and physics had to be extended, and it's been extended in two primary ways. One was the development of special relativity by Einstein in 1905, and the other, about 20 years later, the development of quantum mechanics. And these extended classical mechanics in two different ways. Quantum mechanics extended physics so that it could now apply to very small particles and atoms. And this all fits together now into the broader context of quantum field theory, which is relativistic quantum mechanics. And this is the foundation for modern physics with the exception of gravity. Now briefly, classical physics started with Newton. He integrated terrestrial dynamics, such as the motions of objects falling through the air, with the celestial dynamics, the motions of planets in the solar system. And he unified these with his universal law of gravitation and his laws of motion. so that these two domains of experience could both be understood as specific solutions to very general universal equations. And a particularly important feature of this is that the objects here are described as following very specific trajectories in space and time, such that an object always has a particular location and velocity at any moment in time. Now we can contrast this with quantum mechanics by looking at the atom. In the Rutherford model of the atom, shortly after the structure of the atom was understood to consist of a hard nucleus with electrons around it, the earliest models of the atom were analogous to the solar system. But this was really incorrect, and it breaks down. If classical laws are applied to this kind of model, one obtains inconsistencies. For example, the electron orbiting in a path would radiate energy and spiral down into the nucleus, and you wouldn't have stable atoms at all, and that's obviously not the case. So the classical laws of physics were not predicting what actually happened, so they were failing in this particular kind of system. And they also didn't predict things such as the atomic spectra. There were discrete lines of radiation emission lines, frequencies that were emitted by atoms, and the classical laws couldn't explain that. So this forced physicists to look for new fundamental laws of physics, and the new description of the atom provided by quantum theory is that the electrons don't follow these trajectories, these orbits like planets at all. Instead, they're described in terms of probability distributions. These pictures on the right correspond to different energy states of the electrons in the atom. Some of the more complicated ones are higher energy states, and lower energy states are the more simpler ones at the top. And these different colors correspond to different intensities of probability, so that the white regions are very high probability regions where you're likely to find an electron, and the darker ones are where you're less likely to find the electron. And it's not that the electron has a position, it's more like the probability distribution itself is the solution. Quantum theory was discovered independently around 1925, 1926 by Schrödinger, who developed his famous wave equation there, and Heisenberg, who's perhaps most famous for his uncertainty principle there. And what's important to understand here is that the solutions to this wave equation by Schrödinger are probability distributions. They're not trajectories. And the notions of particles and waves don't have their usual meaning as they do in classical physics. And here's an illustration of how a wave can change from being very localized to being spread out, and then changing from being spread out to being localized. And this corresponds to a particle having a very precise position and a not so precise position. And so the Schrödinger wave equation can describe how this can change throughout time, how an electron can have a very definite position at one point and a not so definite position at another point, which means that it's intrinsically kind of spread out at all times. It never actually has a single value for its position at any moment in time. It's either more or less definite in its distribution of locations. And this is expressed in terms of Heisenberg's uncertainty principle as follows. The delta x is the distribution of its uncertainty in location, and the delta p is the complementary distribution in the uncertainty of its momentum, which is related to its velocity. So this figure shows a very large spread in the position and a relatively narrow spread in velocity or momentum. So we have a fairly accurate idea of how fast the particle is moving, but we don't know exactly where it is very well. But it's key to understand here that at any moment the electron does not ever have a single definite location. It's always spread out to some extent or another, and both the position and the momentum are spread out at least a little bit. So there is no single definite state of the electron at any given time. It may be highly localized, but it's still spread a little bit. And so its state is not a single position, but sort of a combination of different positions. We can represent this in a very simplified way as follows. We can imagine that the electron is either on the right side of the room or the left side of the room. Those are two positions. And the quantum mechanical description permits a combination of these two, so that the electron is neither just on the right or just on the left, but is a combination of the two. The technical term is a coherent superposition. And so you combine the left and the right with various factors, C1 and C2, and you can represent this geometrically as a vector in the space where the left and the right possibilities are two axes of this space. And the blue arrow represents the state. So as the blue arrow moves more towards the left axis, there's a higher probability of it being on the left side of the room. As the arrow moves more towards the right axis, there's a higher probability of it being on the right side of the room. But at any moment, it can be in a combination of both. So it's neither on the right nor on the left, but this mixture of the two, which isn't how we think of ordinary objects. And this may be acceptable for thinking about atoms, but it's really not the way we think about ordinary objects. However, it becomes a problem when we realize that ordinary objects really consist of atoms. So quantum theory in principle applies to them. And as a result, you can have large macroscopic objects also be in these strange combinations of two states. And to illustrate how absurd this is, Erwin Schrödinger developed his famous Schrödinger's cat thought experiment. This, of course, isn't something he actually did. This is merely an imagined scenario to illustrate how ridiculous the implications of quantum theory are if consistently applied to the world. So he imagined this box in which there's an atom, and the atom can be in a superposition of two states, one of which is decayed. It's a radioactive atom, and it can decay. So it's in a superposition of decayed and non-decayed states. And as a result, this Geiger counter, which detects if it's decayed or not, is in a superposition of detecting decay or not. And it's connected to a hammer that breaks the bottle if it detects a decay. So the bottle is in a superposition of broken and not broken. And this bottle is filled with poison which would kill the cat. So the cat is then in a superposition of live cat and dead cat states. And Schrödinger, after presenting this thought experiment, said, well, this is obviously absurd, so something's wrong with how we're understanding quantum mechanics. But this remained mostly a philosophical objection for a number of decades because it really didn't make difference in terms of our measurement results. Whenever we opened the box, we saw a live cat or a dead cat, just as if it had always been that way. So it was sort of brushed under the rug and forgotten for many decades, and most physicists just had an attitude of shut up and calculate, don't worry about these philosophical problems. The theory works. Quantum mechanics worked extremely well. You could make mathematical predictions of what you'd measure, and indeed when you performed the experiments and made the measurements, that's what you'd get. And so it was working. Understanding what it really meant about reality was the problem. But that didn't impede physics itself. However, something very interesting happened. A physicist named John Bell was concerned about some of these problems, and he proved this fascinating and profound theorem, named after him. And what he did was he proved a mathematical theorem that started with the assumptions of locality and realism. Locality is the assumption that events here can't instantly alter distant events over there. And realism is the assumption that properties of objects objectively exist independent of our measurement. So they're really out there and we're just measuring what they are. So these were really two basic assumptions that not only were compatible with common sense, but were compatible with classical physics as well. But what his theorem shows is that these are not compatible with the predictions of quantum theory. In particular, if you assume locality and realism, this puts certain quantitative limits on how correlated distant events can be with each other. And quantum mechanical predictions violate those quantitative limits. So this was a fascinating result because it implied that if quantum mechanics is right, either locality or realism, or possibly both, are not correct. And that really pulls the rug out from under two very basic assumptions about the nature of physical reality. But the question remained, if we actually did an experiment, would the experiment confirm the predictions of quantum theory? Or would it agree with locality and realism? What would be the result if we actually performed this experiment? So about 10 years later, they did this and continued to perform various other versions of the same experiment. And basically what you do, as shown here, is you create a couple particles. Those yellow dots are photons heading in different directions. And the blue circles are polarizers that you can turn to different angles to measure the correlation between these photons. And then you have a detector that basically detects whether the photon passes through the polarizer at a given angle or not. And this is how you experimentally measure these correlations between these entangled photons. And in the graph just below, the straight lines, the V there, is the classical correlation that is predicted by assuming reality is local and real. That's what the correlation ought to be. And the curved line there that's very close to it but different from it is the prediction of quantum theory. And when this experiment has been performed every time, the results of the experiments exactly agree with quantum theory. So Bell's inequality is violated, which means that either locality or realism are false. And this is a really significant result. And what it implies is that, as Niels Bohr said, those who are not shocked when they come across quantum theory can't possibly have understood it. If you dig deep into the meaning of quantum theory, it's going to undermine your conventional notions of what reality is. So the first lesson here is that quantum physics demonstrates our common sense notions of reality are wrong. There are some basic ideas we have about the world that are contradicted by quantum theory. Now I should say that this isn't something that only quantum theory does. Relativity is counterintuitive. Its notions of time and space, time dilation and length contraction and things like this are also counterintuitive. Even classical physics is counterintuitive. We see the sun rise and we see the sun set. We don't feel like we're moving on the Earth, and yet physics tells us that the Earth is spinning around and it's revolving around the sun, and so on. And so in a certain sense, that's counterintuitive. We have gotten used to that counterintuitive idea, despite our immediate experience otherwise. But nonetheless, it is not immediately apparent from our experience that that is the case. It's nothing new in physics that it contradicts our common sense notions of reality, but quantum theory really does this in a much more radical way than any other theory of physics. It's really unprecedented and profound. Now this is also something that we find is true with the mystical teachings. They also challenge our common sense notions of reality and make some, frankly, very outrageous claims from that perspective. Now this doesn't prove that quantum theory and mystics are saying the same thing at all. But what it does do is it says that we can't appeal to common sense as the basis for rejecting mystical teachings. Our common sense ideas of reality are wrong, as shown by quantum theory. So we can't appeal to common sense as a reason for rejecting mysticism. So you could put it this way: quantum theory helps to loosen our attachment to the common sense notions of reality and to open our minds to other possibilities. So if quantum theory is incompatible with our common sense ideas of reality, if our naive realism is incorrect, well, what is correct? What does quantum theory say about the nature of reality? This is really the question of interpreting the formalism of quantum mechanics. It has a mathematical formalism, such as the Schrödinger equation, Heisenberg's uncertainty principle. These mathematical equations make specific predictions that are confirmed in the laboratory, and there's no doubt about that. But the interpretations of quantum mechanics ask a different question. They say, what do these equations mean about the nature of physical reality? What kind of picture can we form of physical reality that is compatible with these equations? And it turns out that there is not one answer to this. We don't know what is the correct interpretation of quantum theory. There are many. There's the Copenhagen interpretation developed by Niels Bohr, and this was, for many decades, a dominant interpretation of quantum theory. There's also the many worlds or relative state interpretation. There's a subjective collapse interpretation, the von Neumann-Wigner interpretation. There's decoherence, objective collapse, consistent histories, transactional interpretation, non-local hidden variables. There are over a dozen of these, and they all say different things about the nature of physical reality. All of these are compatible with the formalism of quantum theory. So there's no scientific consensus regarding which one of these is right, and experiments cannot decide which one of these is right. These are philosophical interpretations. The experiments validate or falsify the equations of quantum theory, not the interpretation. So experiments can't help us decide. If we ask which one is right, we can't answer that question on scientific grounds. We can only make philosophical arguments. It's analogous to interpreting a work of art. This particular piece, what does it mean? What is it implying? What's the significance of this? What does it represent? There's no objective answer to these questions. There are objective things you can say about this painting. It was painted by Jackson Pollock. It's called Blue Pools No. 11. He painted it in 1952. It's a very large painting. It's 7 by 16 feet. In 1973, it was appraised at $2 million. Now it's estimated at $50 million. So there are certain objective things we can say about it. But in terms of what it means, there's no single interpretation of this. There's no right or wrong interpretation of this. This isn't a question that is objectively true or false. So our second lesson here is that quantum physics is compatible with many different interpretations, and there's no right one. And we could say more generally, physics doesn't provide us with one way of understanding reality that is correct. The equations, which are confirmed by experiments, can be interpreted in different ways. So there's not one single way to interpret the equations that is right or wrong. It's open to interpretation. That doesn't mean that the science is right or wrong. It means that the interpretation of the science is right. Now, the equations do put constraints on which interpretations are permissible, but it doesn't narrow those to just a single one. It doesn't uniquely determine a single interpretation. So similarly, the teachings of the mystics have been expressed and interpreted in terms of many different worldviews. There's no right one. There are mystics in all the different religious traditions, and one can find common principles shared by them all. And yet they are expressed and interpreted in terms of different theologies, different cosmologies, different religious traditions, using different language, different terminology, so they can be expressed in different ways, but they have this common core, these shared universal principles that you can say are analogous to the formalism of quantum theory, whereas how they're expressed and interpreted vary from tradition to tradition. And there's no single way of expressing these truths that is the correct one. Now, these revolutions in science and physics, such as quantum theory, also bring up another feature, which is that our ideas of reality change radically whenever there's a new theory in physics. We see this in quantum theory, which undermined many of these basic notions of reality. Locality, realism are challenged by quantum theory. So our conception of what is physical reality changes as our science has evolved. We can see this most simply perhaps with the contrast between the geocentric theory and the heliocentric theory of our solar system. Ptolemy, for many hundreds of years, was considered to provide the correct description of the sun, the planets, and the earth, and our cosmology, with the earth being at rest in the center, and the sun and the moon and the planets orbiting around the earth. Now with Copernicus, this switched so that the sun was at the center at rest, and the earth was put in motion. Now this is a change in perspective. It did not involve actually taking a moving sun and stopping it, and taking a fixed earth and throwing it into motion. This was a change in perspective, a shift in the base of reference. So what's significant here is that in the geocentric theory, the earth was really at rest, and the sun was really in motion. And now suddenly, the sun is really at rest, and the earth is really in motion. So the reality of what is physically happening shifted when the paradigm shifted from geocentric to heliocentric with Copernicus. Now we might say, well, we know now what the case is, that this is the real case. The earth is really moving and the sun is really at rest. But with Einstein, we actually showed that neither one of these is the absolute truth. The laws of physics do not prefer a single preferred reference frame for describing motion. So one cannot say in any absolute sense that an object is at rest or is in motion. One is always free to choose a reference frame in which a given object is at rest. It's that object's rest frame. So motion is really relative, and whether something is at rest or is in motion depends on the frame of reference one chooses. To put it another way, motion and rest don't have objective meaning. They're defined relative to our choice of reference frame. So the point here is that what we consider physically real can shift when our paradigms shift. And this has happened with the Copernican revolution, as we've seen here. It can also happen with other revolutions. With Einstein's theory of relativity, our notions of space and time shifted radically. They were viewed as absolute prior to that, and then after Einstein, they're viewed as relative to each other. And with quantum theory, as we saw with Bell's theorem, the notions of locality and realism are undermined, so that gets shifted. So since this is the case, as physics evolves, our very notions of reality evolve along with it. Who's to say that our current notions of reality are, in any sense, the right ones? In a few decades, we may have a completely different theory of physics that implies a different ontology, a different idea of what is real and what isn't. So this is what philosophers of science call pessimistic meta-induction based on the history of science. You look at history and you say, well, there's no way to justify the conclusion that what our current physics describes as real is the correct reality of the physical world. It may be one interpretation that is compatible with our current theories and has a conventional practical utility, but that does not imply that it has any kind of finality. So our lesson here is that science provides mathematical theories that are compatible with measurements. It doesn't provide us with a true physical view of the world. It provides us with a view of the world that we could say is provisional or conventionally true within a given context, but there's nothing final about it. Just as the theories themselves are provisional, the interpretations that accompany those theories are provisional as well. Similarly, mystical traditions provide teachings that are compatible with our experience, but they don't provide us with a true worldview either. They are relative to the different traditions and the manners of expressing them, and in all the traditions also you have a gradation where you begin the spiritual path with certain teachings about the nature of reality that are relative to a certain stage, and then that gets refined progressively as one moves on, and one leaves behind older views and sees that they're only relevant to a particular context, and then one develops a more refined understanding, and then one eventually leaves that behind and has an even more subtle understanding, and ultimately in the mystical path one leaves behind all of these altogether. So another lesson we can derive from the philosophy of science is that our theories themselves are underdetermined by the facts. So in addition to there being the ambiguity or the possibility of there being many interpretations of a given theory, there's the more fundamental issue that given the data currently at hand, there are actually multiple mathematical formalisms that are compatible with the same data. So for example, let's suppose that we're measuring temperature in a room over time and we get these data points, and we try to develop a theory that explains these changes in the temperature over time. And we look at this graph and we say, well, that looks linear, and we draw a line through it. Sure enough, they perfectly match this line. We draw this nice equation and we say, well, that must be the correct mathematical formalism that represents this data. But in fact, each of our measurements has error bars. There's not perfect precision in the measurement of the temperature at any given moment in time. And so there are actually multiple different equations that are compatible with this set of data. So there's an underdetermination of the theory, namely the equation, from the data. And in fact, we can not only match different lines with the same data, but we could match an infinite number of curves with this same data. Here we have a 6th degree polynomial matching the data just fine. And there's nothing in the data that compels us to select one of these lines over the other or one of these curves over the other. They all are compatible with the same data. Now, as a matter of practice, we're most inclined to select the simplest explanation that fits the data, and that's usually what we do using the principle of parsimony, Occam's or His. We'll choose the simplest equation that is still compatible with the data. It's most likely the most robust theory that matches the data. But as we get more data, we may find that that is violated, and in fact we need to add some second-order terms. We actually get some polynomial that accounts for some subtle effects that weren't understood previously. So the underdetermination actually reflects the open-endedness of science, the fact that there always may be additional data that comes into view that forces us to revise our theories and provide new explanations, new formalisms. So what's key here, though, is that whenever we do make a decision that this is our mathematical formalism, this is not forced upon us. There are always multiple different theories that can match the same data. So our fourth lesson here is that experimental data is compatible with different mathematical theories. And this is, you could say, analogous to contemplative experiences are compatible with different philosophical views and models of the spiritual path. So the point here is that our understanding of our experiences and experimental data requires an interpretive element and a selection from our side of the way in which we are going to understand it and put it in some context, make a theory about it. The data alone is not sufficient to select a particular theory uniquely. So those are 4 lessons that hopefully will shed some light on the nature of scientific knowledge and perhaps suggest some useful connections with mystical philosophy. And these lessons, I would say, provide some more general and robust parallels between general principles of scientific knowledge and mystical forms of knowledge that are deeper than merely selecting superficial parallels between, say, particular interpretations of quantum theory and particular philosophies from mystical traditions. So this talk has focused mainly on the lessons from quantum theory and philosophy of science, since the parallel lessons in the mystical teachings are covered well in many of Joel's talks. So I haven't emphasized so much that part of it. If you're interested in learning more about the Center's mission of demonstrating that the truths of science and the truths of mysticism can be seen as different but complementary ways of viewing the same underlying reality, please visit our website at centerforsacredsciences.org. Thank you.